The ships left port in the darkness before dawn, and by the time the sun rose over the Indian Ocean on December 18th, 2025, they were already ghosts on the horizon. 3 vessels, chartered by Ocean Infinity, the American robotics company that had failed once before in 2018, were now carving through swells that had kept their secret for nearly 12 years. Below deck, in climate-controlled bays that hummed with the sound of cooling fans and hydraulic systems, sat an army of autonomous underwater vehicles, each one a masterpiece of engineering worth more than most people earn in a lifetime. Machines with names like Hugin and Remus that could dive to depths where the pressure would crush a human skull like an eggshell. They were not searching the same coordinates as before. This time, they had something the previous expedition did not have. Something that had emerged from the most unlikely source imaginable. Invisible tripwires made of radio waves that crisscrossed the entire planet like a spider's web. And on March 8th, 2014, when Malaysia Airlines Flight 370 vanished from radar with 239 souls aboard, it had broken those tripwires. The disturbances were recorded, archived, and then forgotten for 7 years, until a retired aerospace engineer named Richard Godfrey decided to look at data that everyone else had dismissed as meaningless noise. What he found would redirect the largest underwater search in human history. The captain of the lead vessel, a Norwegian maritime veteran named Lars Hendrickson, who had spent 3 decades navigating these waters, stood on the bridge with a laptop open to a bathymetric map that showed the ocean floor in terrifying detail. Mountains down there, he thought, taller than anything on land, and trenches so deep that if you dropped Mount Everest into them, the summit would still be a kilometer underwater. The search zone had been redrawn based on Godfrey's calculations, a rectangular box approximately 15,000 square kilometers in area, centered on coordinates that were roughly 500 kilometers northwest of the previous search area. 500 kilometers. In an ocean that covers more than 70 million square kilometers, that difference might as well be the distance between planets. And yet this is where they were betting everything. $60 million of equipment and expertise, all because of radio waves that most people don't even know exist. The technology is called WSPR, which stands for Weak Signal Propagation Reporter, but the acronym fails to capture what it actually is. Imagine thousands of amateur radio enthusiasts scattered across every continent, in basement workshops and rooftop shacks, each one transmitting a low-power radio signal that bounces off the ionosphere, that electrically charged layer of the atmosphere that begins about 80 kilometers above your head and extends upward into space. These signals, weak as they are, can travel halfway around the world by skipping off the ionosphere like stones across water, and when they arrive at a receiving station thousands of kilometers away, the receiver logs the signal strength, the time of arrival, the frequency. Every 2 minutes, 24 hours a day, this network creates a snapshot of radio propagation conditions across the entire planet. It was designed for hobbyists to track how well their signals were traveling, a way for a radio operator in Germany to see if his transmission made it to Australia. But Richard Godfrey saw something else entirely. He saw a detection system. When a large aircraft moves through the sky, it disturbs these radio signals. The metal fuselage, the wings, the engines, all of it acts like a mirror for radio waves, reflecting and scattering them in ways that create measurable anomalies in the WSPR data. Think of it like this. If you stretched thousands of laser beams across a dark room in a perfect grid, and then someone walked through that room, you would see the beams bend and flicker as the person's body intersected them. The WSPR network is that grid, except the grid covers the entire Earth. And on the night of March 8th, 2014, something massive flew through it for 7 hours. Godfrey downloaded the archived WSPR data from that night, millions of transmission records, and began the painstaking process of filtering out the noise. Solar activity, magnetic storms, random interference from power lines and electrical equipment, all of it had to be identified and removed. What remained were anomalies that could not be explained by natural phenomena, disturbances that moved in a coherent path across the Indian Ocean at a speed consistent with a Boeing 777 cruising at altitude. The first breakthrough came when Godfrey cross-referenced the WSPR anomalies with the Inmarsat satellite data, the only other technical evidence of MH370's final flight path. The Inmarsat data, which had been analysed to death by experts from Boeing and the UK's Air Accidents Investigation Branch, showed that the aircraft had continued flying for hours after disappearing from military radar, its satellite communication system automatically pinging a geostationary satellite over the Indian Ocean every hour. These pings, called handshakes, did not contain GPS data or any indication of where the plane was, but scientists could analyze the Doppler shift in the radio frequency, the same effect that makes a siren sound different as an ambulance drives towards you versus away from you, and from that calculate the aircraft's approximate speed and direction. The Inmarsat data had given investigators 2 possible paths, a northern corridor towards Central Asia and a southern corridor into the remote Indian Ocean. Debris that washed up on the beaches of Réunion Island and Madagascar in 2015 and 2016, including a flaperon that was conclusively identified as belonging to MH370, had confirmed the southern route, but the Inmarsat data alone could only narrow the final location to an arc, a curved line thousands of kilometers long, where the plane might have run out of fuel and crashed. Somewhere along that arc, the aircraft had hit the ocean, but where exactly? This is where the WSPR data became extraordinary. Godfrey's analysis showed anomalies that tracked along the southern corridor at times that corresponded almost perfectly with the Inmarsat handshakes. At 2:25 a.m. Malaysia time, an anomaly appeared over the Andaman Sea. At 3:30 a.m., another disturbance was recorded further south, moving at approximately 470 knots. At 5:15 a.m., the signal was over the open ocean, hundreds of miles from any landmass, heading deeper into the void. The final anomaly occurred at 8:19 a.m., the same minute as the last Inmarsat handshake, had coordinates that placed the aircraft approximately 1,500 kilometers west of Australia. in an area of the Indian Ocean so remote that it doesn't even have a name, just a designation on nautical charts. But here is what made scientists sit up and take notice. The WSPR anomalies didn't just confirm the Inmarsat path, they refined it. The handshakes could only tell you that the plane was somewhere along an arc, but the WSPR data provided actual waypoints, specific locations where the aircraft had disturbed the radio web. When Godfrey plotted these points on a map and connected them, they formed a flight path that suggested the pilot had not been flying randomly. The path showed course changes, deliberate turns at specific coordinates that aligned with navigational waypoints used by commercial aviation. Near the Andaman Islands, the tracks suggested the aircraft had turned to follow a route called MH370, an established airway that cuts across the Bay of Bengal. Then, over the open ocean where no airways exist, the path became a straight line toward the South Pole, as if someone had simply pointed the nose south and let the autopilot hold that bearing. This was not the erratic meandering of a ghost flight with an incapacitated crew. This was controlled, intentional. Someone had been flying that plane. The implications were difficult to process. If the WSPR data was correct, if these radio disturbances really were caused by MH370, then the previous searches had been looking in the wrong place. Australia had spent $200 million dragging sonar sleds across 120,000 square kilometers of ocean floor in the original search, and Ocean Infinity had scanned another 112,000 square kilometers in 2018, all based on the Inmarsat data and drift modeling of the debris. They had found nothing, no wreckage, no debris field, not a single rivet or suitcase or seat cushion. The ocean floor in those areas had been mapped in such detail that scientists could see individual boulders, and there was nothing there. Either the plane had defied the laws of physics and somehow flown further than its fuel capacity should have allowed, or the initial search area had been based on flawed assumptions. Godfrey's work suggested the latter. His WSPR-based flight path terminated at coordinates approximately 33 degrees south latitude and 95 degrees east longitude, a position that was not only outside the previous search zones, but in an area where the ocean floor topology was particularly treacherous. The bathymetric data showed a landscape of underwater ridges and trenches, volcanic seamounts rising thousands of meters from the abyssal plain like teeth, and canyons that dropped to depths exceeding 6,000 meters. If the aircraft had come down in one of those trenches, it could be resting at a depth where even the most advanced underwater vehicles would struggle to operate, where the pressure is so immense that steel implodes. But before Ocean Infinity committed their ships and their robots to this new location, before they spent tens of millions of dollars scanning the seafloor in an area that was even more remote and hostile than the previous search zones, they needed corroboration. The WSPR theory was revolutionary, but it was also controversial. Many scientists in the aviation and aerospace communities were skeptical. The WSPR network had never been used to track aircraft before. It was designed for radio propagation research, not aerial surveillance. And the idea that you could retroactively track a specific airplane from 7 years ago using data that was never intended for that purpose seemed almost too good to be true. Critics pointed out that the WSPR signals are affected by countless variables: ionospheric conditions, solar radiation, geomagnetic activity, even the time of day. How could you be certain that a particular anomaly was caused by an aircraft and not by some natural fluctuation in the ionosphere? Godfrey had anticipated these objections. He had run validation tests using known flight paths from other aircraft on the same night, checking to see if the WSPR data showed anomalies where those planes should have been, and the results were promising. He had also collaborated with scientists at universities in Europe who specialized in radio wave propagation, and they had confirmed that the physics supported his methodology. But validation tests and peer review were one thing. Physical evidence was another. That evidence came from an entirely different source and from an entirely different scientific discipline. Not radio waves, but biology. Not invisible signals bouncing off the ionosphere, but tiny crustaceans growing on a piece of metal that had floated in the ocean for 16 months before washing ashore on the beaches of Réunion Island in July 2015. The flaperon, a wing component from the trailing edge of a Boeing 777's wing, confirmed through serial numbers to have come from MH370, the first tangible proof that the aircraft had indeed ended its flight in the Indian Ocean. When French investigators examined the flaperon, they found it encrusted with barnacles, hundreds of them, some as large as a human thumb, their shells still attached to the metal after months of exposure to air. To most people, barnacles are just barnacles, marine fouling, the same crusty growths you see on pier pilings and boat hulls. But to a marine biologist, barnacles are data. They are living archives that record the conditions of the water they grew in, and the barnacles on the MH370 flaperon were about to rewrite the search map. But that story, that remarkable convergence of biology and aviation forensics that would validate Godfrey's radio wave theory and move the search zone 500 kilometers to the north. That story begins with a question that no one thought to ask until it was almost too late. What is the water temperature where these barnacles grew? The barnacles were Lepas anatifera, a species commonly known as the goose barnacle. And when Dr. Gregory Herbert, a paleoclimatologist from the University of South Florida, first saw the photographs of the flaperon in 2015, he knew immediately that those shells contained information that no one was looking for. Herbert was not an aviation expert. He had never investigated a plane crash. His specialty was using the chemical composition of mollusk shells to reconstruct ancient ocean temperatures, to understand what the seas were like millions of years ago when dinosaurs walked the earth. But the principle was the same whether you were analyzing a fossil from the Jurassic period or a barnacle from a modern airplane wing. As a barnacle grows, it secretes calcium carbonate to build its shell, and the ratio of different oxygen isotopes in that calcium carbonate is determined by the temperature of the surrounding water. Warmer water produces one isotope signature, colder water produces another. And because barnacles grow in layers like tree rings, adding new shell material every day, you can slice a barnacle open and read its growth history like a book. Each layer is a page. Each page tells you what the water temperature was on that particular day. And if you know how fast barnacles grow under different conditions, you can construct a timeline. Herbert understood that the barnacles on the MH370 flaperon had witnessed something that no human had seen. They had been there in the water as the debris floated, drifting with the currents for 477 days before the flaperon came ashore. They had grown through monsoons and calm seas, through tropical heat and the relative cool of the southern Indian Ocean, and their shells had recorded all of it. If he could analyze those shells, he could determine what temperatures the flaperon had experienced, and if he could match those temperatures to specific regions of the Indian Ocean, he could potentially trace the debris backward to its point of origin. There was just one problem. The flaperon was in France, locked in a secure facility where French aviation authorities were conducting their own analysis, and they were not inclined to let an American scientist they had never heard of start drilling holes in what was considered evidence in an active investigation. Herbert spent months trying to get access. He wrote letters, made phone calls, reached out to colleagues who might have connections to the French Bureau of Inquiry and Analysis for Civil Aviation Safety. Nothing worked. The bureaucracy was impenetrable, and with every passing month, the flaperon sat in storage while the barnacles attached to it slowly dried and deteriorated. By the time Herbert finally got approval in late 2016, nearly a year and a half after the flaperon had been recovered, some of the barnacles had already been removed and discarded, but enough remained. He was granted permission to take samples from 5 specimens, not the whole barnacles, but thin cross-sections that could be extracted without significantly damaging the evidence. Herbert traveled to France with a portable lab setup, a precision saw that could cut through shell material without shattering it, and an electron microprobe for measuring isotope ratios. The work was delicate. Each barnacle had to be removed from the flaperon with surgical precision, then sectioned along its growth axis to expose the internal layers, then polished to a mirror finish so the microprobe could read the chemical signature of each layer. Under the microscope, the cross-section of a barnacle shell looked like a geological formation. Bands of light and dark material stacked in irregular patterns, each band representing a period of growth. The youngest material was at the outer edge, the material that had been deposited just before the flaperon washed ashore, and the oldest material was at the center, the very first layer the barnacle had secreted when it first attached itself to the metal surface. Herbert began with that oldest layer. If he could determine the water temperature when the barnacle first colonized the flaperon, he could infer what part of the Indian Ocean the debris had been floating in at that time. The microprobe scanned across the innermost band of shell material, measuring the ratio of oxygen 18 to oxygen 16 with atomic precision. And when Herbert ran the calculation to convert that ratio into a temperature, the result was 27 degrees Celsius. 27 degrees, that was warm. Not just warm for the Indian Ocean in general, but warm for the area where everyone had been searching. The previous search zones, the areas that had been scanned by Australia and Ocean Infinity based on the Inmarsat satellite data, were located at approximately 35 to 38 degrees south latitude, a region where the Indian Ocean is influenced by the Antarctic circumpolar current, where the water is cold. In March, when MH370 disappeared, the sea surface temperature in those southern search zones would have been between 18 and 22 degrees Celsius, not 27. 27 degrees was the temperature you would find much further north, in the tropical and subtropical waters above 30 degrees south latitude, hundreds of kilometers away from where anyone had been looking. Herbert double-checked his measurements. He analyzed the other barnacle samples, running multiple scans on each one to ensure the data was consistent. Every sample told the same story. The barnacles had begun their life cycle in warm water, and as they grew, as the flaperon drifted with the currents over the following months, the temperature signatures in their shells showed a gradual cooling, consistent with debris moving southward into cooler waters before eventually being caught in the westward flowing currents that carried it toward Réunion. But that initial temperature, that 27-degree reading from the innermost shell layers, was the key. It meant the flaperon had entered the water in a location far warmer than the crash sites that had been hypothesized. When Herbert published his findings in 2017, the reaction from the aviation investigation community was mixed. Some experts were intrigued. The barnacle data was solid science, peer-reviewed and reproducible, and it suggested that the drift models used to predict where debris might have originated were incomplete. Those models had been based on surface current data and wind patterns, but they had not accounted for subsurface currents or the biofouling characteristics of different species. Other experts were dismissive. They argued that barnacles were too variable, that water temperature alone could not pinpoint a crash site because the flaperon could have drifted through multiple temperature zones, that Herbert's methodology, while scientifically valid, was being applied to a problem it was never designed to solve. But then someone noticed something remarkable. Richard Godfrey, the same engineer who had been analyzing the WSPR radio data, saw Herbert's paper and realized that the barnacle temperatures corroborated his own findings. The WSPR-derived crash location that Godfrey had calculated, those coordinates at 33 degrees south latitude, placed the aircraft in a region where the March sea surface temperature was approximately 26 to 27 degrees Celsius. The match was almost perfect. Two completely independent lines of evidence, one based on radio wave physics and the other based on marine biology, were pointing to the same general area. This was not a coincidence. This was convergence. Godfrey reached out to Herbert, and together they began comparing their data in detail. Herbert provided temperature profiles for different regions of the Indian Ocean, showing where you would expect to find 27-degree water in March, and Godfrey overlaid those temperature zones onto his WSPR-derived flight path. The intersection of the two datasets created a target zone, an area of approximately 15,000 square kilometers where both the radio anomalies and the barnacle temperatures aligned. It was still a vast area, larger than the country of Qatar, but it was dramatically smaller than the original search zone, and more importantly, it was in a completely different part of the ocean. Ocean Infinity was paying attention. The company had been stung by their failure to find the wreckage in 2018, and they had continued monitoring new developments in MH370 research, looking for any data that might justify a second attempt. The combination of WSPR and barnacle evidence was compelling, but it was not quite enough to commit to another multi-million-dollar expedition. They needed one more piece of the puzzle. They needed to understand not just where the plane had crashed, but how. Because the manner in which MH370 had hit the ocean would determine what kind of debris field they should expect to find, and where exactly within that 15,000 square kilometer zone they should focus their search. A high-speed impact, the kind that occurs when an aircraft runs out of fuel and enters an uncontrolled dive, would create a wide debris field scattered over several square kilometers. The plane would disintegrate on contact with the water, and wreckage would be spread across the surface before sinking. Some of that wreckage would float, carried away by currents, which is why pieces of MH370 had washed up on distant shores. But much of it would sink relatively quickly, especially the dense components like engines and landing gear, and those pieces would settle on the ocean floor in a pattern radiating outward from the point of impact. Previous search operations had assumed this scenario. They had looked for debris fields, for scattered wreckage that would show up on sonar as distinct objects against the seafloor. But what if the impact had not been catastrophic? What if someone had been controlling the aircraft all the way to the surface, executing a controlled ditching in the same way that Captain Chesley Sullenberger had landed US Airways Flight 1549 on the Hudson River in 2009? A controlled ditching would produce an entirely different signature. The aircraft would remain largely intact, and instead of disintegrating across a wide area, it would sink as a single object, possibly staying in one piece until it hit the bottom. The debris field would be compact, maybe just a few hundred meters across, and if the plane had sunk in deep water, in one of those abyssal trenches where the ocean floor drops to 6,000 meters, it might be buried in sediment or wedged into a crevasse where sonar would struggle to detect it. This question, controlled ditching versus catastrophic impact, had been debated since the beginning. Boeing engineers who examined the flaperon and other recovered debris argued that the damage patterns suggested a high-energy impact. The flaperon's trailing edge was crushed, the composite materials shattered in ways consistent with hitting the water at high speed. But other experts pointed out that much of the damage could have occurred after the crash as debris tumbled in the waves or was battered against rocks when it washed ashore. There was no definitive evidence either way. Then, in 2021, a researcher named Vincent Line, an adjunct scientist at the University of Tasmania who specialized in deep-sea geology, published a paper that reignited the entire debate. Line had been studying the bathymetric data from the Indian Ocean, the detailed maps of the seafloor that had been created during the original search operations, and he had noticed something that everyone else had apparently missed. There was a hole in the ocean floor, not a natural geological feature like a volcanic crater or a collapsed lava tube, but a long, narrow, steep-sided trench that cut through the abyssal plain like a scar. Line identified it as a possible location for the wreckage based on a theory that was both elegant and disturbing. He believed that the pilot of MH370, Captain Zahari Ahmad Shah, had not only flown the plane deliberately into the remote Indian Ocean, but had specifically chosen to crash it in a location where it would never be found. And the best place to hide an aircraft, Line argued, was not on the flat abyssal plain where sonar could easily detect it, but in a deep, narrow trench, a geological feature so specific and so remote that searchers would never think to look there unless they knew exactly where it was. The feature Line identified was called Broken Ridge, a massive underwater plateau that rises from the deep ocean floor approximately 1,500 kilometers west of Australia. Broken Ridge is a remnant of an ancient tectonic plate that rifted apart millions of years ago, and its edges are marked by steep escarpments and fault lines where the crust has fractured and collapsed. One of these fractures, which Line referred to as the Penetrator hole, was a narrow canyon approximately 6 kilometers long and up to 6,000 meters deep. Its walls were nearly vertical in some places, and the canyon floor was littered with rockfall and sediment. Line's theory was that Captain Zahari had researched the bathymetry of the Indian Ocean before the flight, studying the seafloor maps available from geological surveys, and had identified Broken Ridge as the ideal location for a vanishing act. If he could glide the aircraft down into that canyon, a controlled water landing that kept the plane mostly intact, the wreckage would settle into a crevasse or become wedged between the canyon walls, effectively invisible to sonar scans conducted from the surface. It sounded like a conspiracy theory. The idea that a commercial airline pilot would meticulously plan not just the destruction of his aircraft, but the permanent concealment of the evidence was difficult for many people to accept. But Line had data to support his hypothesis. He pointed to the flight simulator found in Captain Zahari's home, which had been seized by Malaysian police after the disappearance. Forensic analysis of the simulator's hard drive had revealed that Zahari had practiced a route that closely matched the suspected path of MH370, flying northwest from Kuala Lumpur, then turning south over the Andaman Sea and continuing into the southern Indian Ocean until the simulated aircraft ran out of fuel. The simulator data had been reported in the media, but Malaysian authorities had downplayed its significance, suggesting it was just one of many routes Zahari had experimented with. Line disagreed. He argued that the simulator route was a rehearsal, and when he compared the endpoint of that simulated flight to the location of Broken Ridge, he found they were within 100 kilometers of each other. Line also examined the debris that had been recovered from MH370, particularly the flaperon and a section of the outboard flap that had washed ashore in Tanzania. His analysis of the damage patterns led him to conclude that both control surfaces had been in a deployed position when the aircraft hit the water. Deployed flaps and flaperons are used during landing to increase lift and slow the aircraft down, and their deployment in this case suggested that someone had been actively controlling the plane during its final descent, trying to make a soft landing rather than letting it plummet out of control. This contradicted the prevailing theory that MH370 had spiraled into the ocean after running out of fuel with an incapacitated or dead crew. But even if line was correct, even if Captain Zahari had deliberately flown the plane to Broken Ridge and ditched it in the Penetrator hole, there was still the question of whether the wreckage could be found after nearly 12 years on the ocean floor. Metal corrodes, structures collapse under pressure, and silt accumulates at a rate of several centimeters per century in the deep ocean. A Boeing 777 is a large aircraft, but it is not indestructible, and if it had landed in the Penetrator hole, it would have been subjected to pressures exceeding 600 atmospheres, forces that could crush sealed compartments and cause structural failure over time. Ocean Infinity believed they could still detect it. Their autonomous underwater vehicles were equipped with synthetic aperture sonar, a technology that creates high-resolution images of the seafloor by processing multiple sonar returns from slightly different angles. This technique could distinguish between natural geological features and man-made objects, even when those objects were partially buried or obscured by sediment. The vehicles could also operate at depths exceeding 6,000 meters, and they could navigate through complex terrain, following the contours of the canyon walls and scanning into crevasses where a traditional towed sonar array would never reach. In December 2024, Ocean Infinity announced they were returning to the search. They had secured funding from a consortium of private investors and insurance companies who stood to benefit if the wreckage was found and the cause of the disappearance confirmed. The new search would focus on the area identified by the convergence of WSPR data, barnacle temperature analysis, and LINE's geological research. The expedition would deploy 8 autonomous underwater vehicles simultaneously, each one capable of scanning 100 square kilometers per day, meaning they could cover the entire 15,000 square kilometer target zone in less than 3 weeks if conditions were favorable. But favorable conditions in the Indian Ocean are rare. The area is notorious for violent storms, swells that can reach 15 meters in height, and unpredictable currents driven by the interaction between warm tropical water flowing south and cold Antarctic water moving north. The search would need to be conducted during the Southern Hemisphere summer between December and February, when the weather was relatively calm, and even then there would be days when the ships would have to suspend operations and wait for the seas to subside. The ships departed from Fremantle, Australia on December 18th, 2025 and reached the search area on December 22nd after 4 days of transit. By Christmas morning, the first autonomous vehicles were in the water, descending into the darkness, their lights and cameras useless in the absolute blackness of the deep ocean, navigating only by sonar and inertial guidance systems. The vehicles would spend up to 72 hours underwater on each mission, methodically scanning back and forth across the designated search lanes like a lawnmower cutting grass. And when their batteries ran low, they would automatically ascend to the surface to be recovered and recharged. The data they collected, terabytes of sonar imagery and bathymetric measurements, would be transmitted to the ships and processed by a team of analysts working in shifts around the clock. Every anomaly would be flagged, every shadow and echo that could possibly be debris, and if something promising was detected, a vehicle would be sent back down to conduct a closer inspection, using its cameras to capture video and still images of whatever lay on the bottom. As of today, January 23rd, 2026, the search has been underway for 5 weeks. Approximately 40% of the target zone has been scanned, and while several interesting features have been identified, including what appears to be a World War II-era shipwreck and a scattering of geological formations that resemble crashed aircraft until examined more closely, no definitive sign of MH370 has been found. But the most promising area, the Penetrator hole at Broken Ridge, where Vincent Line believes the wreckage lies hidden in a geological tomb carved by tectonic forces millions of years before humans even existed. That area has not yet been searched. It is scheduled for late January and early February, when the vehicles will descend into that narrow canyon and sweep their sonar beams across its walls and floor, looking for the unmistakable shape of a Boeing 777, or even just a piece of one. Anything that would confirm they are looking in the right place. But there is another possibility that no one wants to discuss openly, a scenario that keeps the search coordinators awake at night and makes them double-check their data before launching each mission. What if the convergence of evidence, the WSPR signals and the Barnacle temperatures and the geological analysis, what if all of it is correct, but the plane is simply not detectable? What if it broke apart on impact despite being controlled, and the pieces are scattered across a debris field so diffuse that sonar cannot distinguish them from the natural clutter of the seafloor? What if it sank into mud that has since covered it completely, or wedged itself into a fissure so narrow that the sonar beams pass over it without registering an anomaly? Or what if, and this is the possibility that is almost too terrible to consider, what if everyone is still looking in the wrong place? There is a possibility that must be spoken aloud now. A truth that exists alongside all the data and theories and carefully analyzed evidence. And that truth is this: the ocean may never give back what it has taken. The ships above are searching, their robots descending through layers of water that grow colder and darker with every meter, their sonar pulses reaching out into the void like fingers searching for something that may no longer wish to be found. But the Indian Ocean is not obligated to answer. It has kept secrets before, ships that vanished centuries ago, entire civilizations swallowed by tsunamis whose ruins lie beneath sediment that has accumulated for thousands of years. If Ocean Infinity completes their search and finds nothing, if they scan every square kilometer of the target zone and detect only the natural topology of the seafloor, the mystery does not end. It simply returns to where it has always been, suspended in the deep, waiting in the silence. 6,000 meters below the surface, where the search vehicles are moving through water that has not seen sunlight in millennia, the environment is not hostile. It is simply indifferent. The pressure at this depth is 600 times greater than the air pressure at sea level, a force so immense that it would compress a human body to the size of a briefcase in seconds. But the water itself feels nothing. It is neither warm nor cold in any way that matters. The temperature hovers just above freezing, a constant 2 degrees Celsius that never changes, not with the seasons, not with the passage of years. There are no storms here, no currents strong enough to move anything larger than a grain of sand. The abyssal plain is a place of eternal stillness. The darkness is absolute, not the darkness of a moonless night where your eyes might adjust and begin to perceive shapes, but a darkness so complete that the concept of sight becomes meaningless. No light has reached this depth since the ocean formed. The only illumination comes from bioluminescent creatures that drift past like tiny stars, jellyfish trailing curtains of light, deep-sea fish with lanterns growing from their foreheads, bacteria that glow faintly on the edges of decaying matter. But even these lights are rare and brief, and they do nothing to illuminate the vastness that surrounds them. If the wreckage of MH370 rests here, it rests in darkness that no human eye will ever witness directly. There is something falling through the water column above, always falling, so slowly that it would take weeks to descend from the surface to the bottom. Scientists call it marine snow, and it is not snow in any traditional sense, but a constant gentle rain of organic particles, the remains of plankton and algae that died in the sunlit waters far above, their tiny bodies drifting downward through the darkness, accumulating, settling, creating a layer of sediment on everything below. Over the course of 12 years, this marine snow would have covered any wreckage with a fine dust, a white powder that would soften the edges of metal, fill the hollow spaces, blur the boundaries between what is aircraft and what is seafloor. The Boeing 777, if it is here, would no longer look the way it did when it left Kuala Lumpur. The bright red and blue livery of Malaysia Airlines would be invisible under the accumulation. The windows would be dark. The wings might still be recognizable, their shape distinct even under the covering of sediment, but they would be draped in this eternal snowfall, weighted down, becoming part of the landscape. There are creatures here, not many, but they exist in numbers that would surprise anyone who imagined the deep ocean as lifeless. Amphipods the size of your hand, scavenging across the seafloor in slow motion. Sea cucumbers that move so gradually, their progress can only be measured over days. Brittle stars with arms that reach out to catch the falling particles of marine snow. If there is wreckage, these creatures would have found it within weeks of its arrival. They would have explored every surface, colonized every crevice, transformed it from a foreign object into habitat. After 12 years, the aircraft would not be an intrusion anymore. It would be part of the ecosystem, as natural as the volcanic rocks and the ancient sediment. The water itself is ancient. Some of the molecules suspended here in the deep Indian Ocean have been circulating through the world's oceans for thousands of years, flowing in currents so slow they are measured not in meters per second, but in meters per decade. This water was here before humans built cities, before we learned to fly, before we even understood what an ocean was, and it will be here long after the search ships have departed, long after the autonomous vehicles have been recovered and returned to port, long after the last person who remembers MH370 has themselves passed into memory. The ocean does not count time the way we do. Above, on the surface, the search vessels are loud. Their diesel engines throb, their generators hum, their crews move across the decks, speaking into radios and checking readouts on computer screens. But the noise does not penetrate. By the time you descend 100 meters, the sounds of the surface world have faded to nothing. And by the time you reach 1,000 meters, there is only the occasional click of a whale in the distance, the faint crack of shifting ice from Antarctica, hundreds of kilometers away. At 6,000 meters, there is silence. Not the silence of an empty room, but the silence of a place so far removed from the world of sound that even the concept becomes abstract. The wreckage, if it is there, rests in this silence, weightless in the water despite its mass, suspended between the surface and the seafloor, or perhaps already settled, already at rest. The families of the 239 people who are aboard Flight 370 have waited 12 years for an answer. Some have accepted that the answer may never come. Others continue to hope that the ocean will yield its secret, that a robot will transmit an image back to the surface, showing something unmistakable, a wing, an engine, a piece of fuselage with a serial number that matches the records. But whether the wreckage is found or not, whether the search succeeds or joins the long list of mysteries that remain unsolved, the ocean itself remains unchanged. It does not judge. It does not remember. It simply exists. Vast and dark and eternal. The Penetrator hole at Broken Ridge is waiting. That narrow canyon carved into the seafloor by forces that dwarf anything humans have ever created, its walls rising vertically through thousands of meters of water, its floor hidden in shadow even from the sonar that will soon sweep across it. If Vincent Line is correct, if the pilot of MH370 chose this place deliberately, then the aircraft rests in a tomb that was prepared millions of years before it was needed. A perfect hiding place, a perfect grave. But perhaps that is not the right word. Grave suggests something final, something closed and sealed away from the world. The deep ocean is not like that. It is not death. It is simply another form of existence. Slow, cold, dark, but not empty. Not silent in the way we understand silence. There is life here, movement here, continuation here. The search will conclude in the coming weeks. Either the robots will find what they are looking for, or they will surface for the last time with their cameras and sonar showing nothing but the natural contours of the Earth. Either way, the ships will eventually turn back toward Australia, their crews exhausted, their mission complete or abandoned. And the Indian Ocean will remain exactly as it has been, exactly as it will always be. The waves on the surface will continue to rise and fall, with the rhythm of storms and calms that have repeated for billions of years. The currents will continue their slow circulation, carrying water from the tropics toward the poles and back again in cycles that take centuries to complete. And far below, in the darkness and the cold and the pressure, whatever rests there will continue to rest. Undisturbed, unknown, at peace. Good night.